A very good morning to all my fellow friends. Today I'm going to talk about my research work on with the title Elucidating the Spatial, Temporal, and Seasonal Variability of Ground Level Ozone in Malaysia using Backward Trajectory. So this is a collaboration work with my counterparts from UKM and also researchers from Kyoto University. This is the outline of my presentation. I will start with the introductions. I will talk about what is tropospheric ozone and why is it important to study ozone pollution. And follow that is we'll talk about the study area and the period, and then follows by the method. And then I will continue with results and discussion and conclude my presentation with some take-home messages. So when we talk about ozone in our community, we basically refer to two types of ozone, whether it's a good ozone or bad ozone. The good ozones are the stratospheric ozone because these ozone are at a high level and is produced because of the Chapman cycle. And it's called good ozone because it protects the Earth from the UV radiations. But when we say about the tropospheric ozone or the bad ozone, these are the pollutant because they are secondary pollutant, which has important implications on atmospheric chemistry and also air quality degradations. So basically it's not directly emitted, but it's produced because of the complex reactions between the VOC and also the NOx under the presence of sunlight. And the problem statement why ozone pollution is important because it's crucial for us to understand how climate change influenced the air quality at a regional scale because it's not directly emitted. That's why it's very difficult for us to understand why one place has ozone pollution but the other doesn't have. So that's why the ozone pollution or the ozone study is ongoing research because when the global climate change and it can affect the monsoon variability, when it affects the wind patterns and also the monsoon, basically the ozone pollution can also be impacted. And by doing this kind of local studies are imperative for accurately and robustly assessing these impacts because they can, with these findings, we can actually bring to the policy making and also the local authorities for better urban planning. So this is my study area is in Malaysia. So we have gathered a total of 43 stations. The central zone with 7 stations, the north zone 12 station, the south zone 7 station, the east zone 9 station, and Borneo 9 station. So basically, all the stations that across the country have been selected to better understand how ozone occurs in Malaysia. So these are the details of the station. For example, North Zone is consisted of Perlis, Kedah, Pulau Pinang, Perak, and Central Zone is comprised of Kuala Lumpur, Putrajaya, Selangor, and Negeri Sembilan. The South Zone is from Malacca and Johor. East Zone, Pahang, Terengganu, Kelantan, and Borneo, of course, is Sabah and Sarawak. The study period that we have selected to look at this in our study is 2017 to 2020. The reason why we are selecting this because in before 2016, Malaysia's air quality station is actually handled or regulated by ASMA, and beginning 2017, the Ministry of Environmental in Malaysia has decided to change from asthma. I mean, they have appointed PSTW as our new contractor. That's why we are selecting year from 2017 to 2020. And then because after 2020, Malaysia, I think the global has been affected by COVID-19. And in order to eliminate the effects of the movement control, okay, so we decided to cover only 4 years from 17 to 20. So there are the four. Malaysia's climate is actually tropical climate, but we are still subject to some monsoon variability. The well-known ones are the southwest monsoon, which covers from May, June, July, and August, and the northeast monsoon is from December November, December, January, and February. So there are also another two monsoon, or we call it intermonsoon, covers from March to April. So IN1, intermonsoon 1, and IN2, intermonsoon 2, from September to October. So the method that we use is basically we use all the raw data from PSTW, and then they provide in an hourly basis. And then for the ozone, because this is our main targeted study, so we have calculated the daily 8-hour maximum using the 8-hour average that has the largest within that day. In cases where fewer than 8 hours ozone values are available, then we will the 8 hours maximum ozone will be assigned as a missing value. And for nitrogen dioxide, we are going to calculate the daily average NO2 using all non-missing hourly average available for the day. And this protocol is also applied to other pollutant like SO2, uh, uh, NO, and also other meteorological parameters like temperature, relative humidity, wind speed, and wind directions. So we have the three main calculations here involved. We are using hourly average. This will help us to do the diurnal analysis. And daily average, of course, is important because we want to. And for the daily average, we have a daily maximum 8 hours for ozone, daily average NO2, and the daily average meteorology variables, for example, the temperatures, wind speed, wind direction, RH, and the solar radiations. And for monthly average, actually we average for annual and also for seasonal characteristics. And for the high split model, this model is used to track um, the backward trajectory or the origin of the air mass. So we are using 4 days of backward trajectory, which has 96 hours, and is driven by GDAS, the Global Data Assimilation System, which has a time step of 3 hours and 1 degree by 1 degree, approximately 120 kilometers. And the vertical grid spacing has 23 pressure levels between 1000 to 20 hectopascal. And then the model is initialized at 00 and also 12 UTC for each 96 hours runs. So this is a result. We can see we have 5 zones: the north, central, southern, and eastern, and Borneo. So we can see that the central ozone, which is indicated by the blue color dots or the blue lines, and then the red color represents the daily average and NO2. So we can see that the central zone has the highest daily 8 hours maximum, around 63 ppb, and and also have a highest daily average NO2, which gives us 14 ppb. And the trend in the daily 8 hours maximum ozone is also increasing, despite the decreasing NO2 trend, especially in the central zone. And this trend is actually is not observed in other zones. And then we hypothesize that this is indicating a VOC limited region where the ozone pollution is much more controlled by the VOC instead of NOx. And this is the table for the statistics. We calculated the number of days with the moving daily average 8 hours ozone with greater than 60 ppb. This is because this is the standard for the ozone pollution. And then for central, northern, southern, eastern, and Borneo, so we calculated the number of days which has greater than 60 ppb, and we found that uh, the highest numbers is actually come from central zone, okay, followed by northern, southern, eastern, and Borneo. And we can also see that the central zone is favors the VOC limited region because of the patterns in the ozone and also the NOx. And Borneo zone basically is favoring the NOx limited region, which means that when we reduce NOx, basically we can reduce the ozone pollution in the border zone. But this is the opposite for the central. So when we reduce the NOx in central zone under the VOC limited region, this might increase the ozone pollution or the ozone concentration in the central zone. And for the meteorological variability, we look at the temperatures and the wind pattern. So our findings actually shows that the central zone is characterized by the high daily average air temperature. In fact, it also has the highest among these 5 zones and very low daily average wind speed, which is around 1 meter per second. And under this condition, it actually favors the ozone formation due to the increased photochemical reaction and also reduced pollutant dispersion. And we think that this pattern, this increasing air temperature and reducing wind speed, is because of the UHI, or the urban heat island effect, where urbanization exacerbates the meteorological conditions conducive for ozone formation through the UHI effect. And this effect is also most significant in the central zone because the central zone is the highly and also the most populated region in Malaysia. For the seasonal variability, because Malaysia is characterized by the tropical climate, that's why we cannot see the ozone has a very, how to say, very pronounced variations throughout the years. Okay, but still we can see that the central zone exhibited a bimodal distribution where we can see the peak in the March and April and also September to October, coinciding with the biomass burning season in the neighboring regions, for example, the Indochina and the Sumatra. And these biomass burning events can actually transport the pollutants, including the ozone precursors, over long distances, and that's why influencing the regional air quality in Malaysia. And we also use MIRA tool to look at the regional scale of the monsoon variability. So we can see that during the northeast monsoon, the northeasterly flows are strongest, where the Siberia high pressure system exits over the coastline of East China before reaching to the Western Pacific Ocean, as we can see from here in Figure A. And intermonsoon 1 is characterized by moderately northeasterly winds and begins when the anticyclone system reaches to the Western Pacific Ocean, where the northeasterly flow is slackened. And climatologically, IM1, or the intermonsoon period 1, is also the hottest month of the year in the Maritime continent. Now I show you the precipitation. This figures is plotted using the global precipitation satellite data, and we also do the same for 4 periods: the northeast monsoon, intermonsoon 1, southwest monsoon, and also intermonsoon 2. So we can see increased rainfall is observed on the windward side of the Maritime continent. And when there's a rainfall, the ozone pollution is less likely to occur in during northeast monsoon in ozones. You can see that less than 15%, and except for the central zone, which gives us around 44%. This is the number of ozone pollution days. And among the 5 zones, the central zone has the highest ozone pollution occurrence with 58%, and the mean of the MDA8 ozone is reaching 74 ppb during IM1, which is quite severe because this actually exceeds the standard, the national standard, and also the WHO standards. And IM1 is characterized by the moderate northeasterly flow and begins when the anticyclone circulation reaches to the Western Pacific Ocean. This figure shows the backward trajectory in Shah Alam during intermonsoon 1 because intermonsoon 1 has the highest ozone pollution occurrence. That's why we selected this period. And also we selected Shah Alam because it represents the central zone. And by comparison, we also look at during southwest monsoon at the same station in Shah Alam. And another zone that has a high ozone pollution is the north zone. So we selected Seberang Jaya as our target station. during southwest monsoon and also northeast monsoon. Okay, for comparison. So we can see that IM1 and IM2 occurring from March to April and September to October, respectively. These monsoons are the transitional periods, and they are characterized by moderate and strong wind flows and variable precipitations pattern. And we can also see that, especially in IM1, in this figure, we can see that they are uh, the air mass trajectory shows that the air mass actually comes from uh, the northeast direction, and also some come from the Indochina. And the red color or the red dots here actually represent the MODIS fire count, which we calculated from MODIS C6, the collection 6. So when there is a heavy, a high fire counts, of course the 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 smoke plume is high, and because of the northeast monsoon, that's why it's possible to bring all these pollutants from Indochina to Malaysia, and particularly affecting the ozone pollution in Shah Alam or in the central zone. And for we also look at another station in Pasir Gudang during IM2 and also southwest monsoon. Basically, we want to compare what are the trajectory during these two seasons at the south zone. So we see that IM1, IM2 occurring during this, and then most of the especially in IM2 during September and October, we can see that most of the trajectory actually come from Kalimantan and also Sumatra. And during these months, this September and October is also well-known biomass burning season in Indonesia. And that's why we can also observe a high possibility that the air mass from this country, from this region, Sumatra and Kalimantan, they are possible to bring the ozone precursors from the biomass burning area towards the north zone, towards the south zone of Malaysia. And in southwest monsoon, occurring from May to August, is characterized by westerly to southwesterly winds, and there are also drier conditions, which facilitate the long-range transport of the pollutants, including the biomass smoke from regions like Sumatra and Kalimantan. And this period actually affect the ozone concentration in the northern and the eastern zone, where transboundary air pollution from biomass burning significantly impact the regional air quality, as we can see from these backward trajectory high-speed modeling results. And finally, this is some of the take-home messages from this paper. So during the inter-monsoon period IM1, the central zone experienced frequent unhealthy ozone levels, with the highest daily 8-hour maximum ozone recorded at 74 ppb, and accompanied by elevated daily average NO2, 27 ppb. And despite the decreasing annual NO2 concentration, the ozone concentration shows an increasing trend. This reflects a VOC limited region, exacerbated by the warming trends observed across central, northern, and southern zone. Where we look at the trend, we can see that in these three zones, the temperature has been increasing per year is 0.12 to 0.24 degrees Celsius. And ozone concentration exhibited a bimodal peak in the March and October. This is because of the biomass burning season in Peninsula Southeast Asia, which is the Indochina, consists of Cambodia, Vietnam, and also Thailand. And insular Southeast Asia is from Indonesia, mainly come from Kalimantan and Sumatra. So from the backward trajectory, we can summarize there are 3 points here, 3 major points. The northeasterly flow from the Indochina and East China can affect the central zone during the intermonsoon 1 season, and the southwesterly flow from Sumatra impacting the northern zone during the southwest monsoon, and the southwesterly flow carrying biomass smoke from Sumatra affecting the southern zone during IM2, intermonsoon period 2. And these also possibly influenced by large-scale climatic phenomena such as ENSO and MJO. So this is the acknowledgement. We would like to thank the Malaysia Department of Environment, DOE, for providing the air quality and the meteorological data. And then we also greatly thank the NASA MIRA 2 reanalysis and the precipitation data, providing the regional meteorology for investigation in this study. And with that, I end my presentation here. So thank you for your attention.